screen. Okay, all of you present. Okay, previously, for previous class, we covered the definition of Newtonian fluid. Yeah? Newtonian fluid, what I mean by Newtonian fluid? When you heard about the word Newtonian, you have to call two equations. One is shear stress. Shear stress equal to F divided by A, force divided by area. And the direction of the force must parallel to the area. Yeah. And for the shear rate, and second equation you should call when you defining or give definition to a Newtonian, you should call the equation for shear rate. Shear rate is you change du over dy, means the change of displacement u divided by the change of y direction. So when it's the Newtonian, these two equation is proportional, right? Shear stress proportional to the shear rate. So in short, you put in an unknown or constant value, will give you shear equal to viscosity times the shear rate. Yeah. So this equation define what is the Newtonian. As long as the fluid meet the criteria that the fluid shear stress is proportional to the shear rate, then it's fall under Newtonian. Yeah. So today we look at another definition for non-Newtonian. Okay. Now, what is non-Newtonian? Newtonian means the shear stress is not proportional to the shear rate. Yeah. So example is your toothpaste is a non-Newtonian. Another example is a pen, also non-Newtonian. Yeah. Okay. So this is the answer for your tutorial question, chapter 1, question 21. Yeah. So we ask you what is the definition for non-Newtonian fluid. Yeah. So under non-Newtonian fluid, usually we look at two behavior. One is time independent, which means the behavior doesn't change towards time. Another one is time dependent. So we have two. So there's a two graph on the screen now, same like in your handout. So on the left and right is a little bit different. The axis is different. So if you look at the graph A on the left, the axis, the y-axis or vertical axis is shear stress. The horizontal axis is deformation rate or shear rate. So if you look at here, you have four lines here. You will see that if the line is proportional or in a linear behavior, y equal to mx plus c, the behavior, so you will have a Newtonian. So under non-Newtonian, you have dilated and also pseudoplastic. These two is non-Newtonian. And for Bingham plastic, you see there's a straight line. So this one is, can say, behave Newtonian behavior. Huh? So because it's having a straight line, although it starts with some value of your shear stress. Yeah. On the right-hand side graph, you will see there's a graph with two axes, a different axis. The vertical one is the viscosity versus the deformation rate or shear rate. So you will see that for Newtonian, the viscosity always constant. However, for non-Newtonian, pseudoplastic and dilated fluid, then it is not a straight line. Okay, the viscosity is not straight line. Okay, so this graph, they will explain what is Newtonian or is non-Newtonian. Okay, so chapter 1, one of the main point is you able to differentiate or define, give definition to Newtonian fluid and non-Newtonian fluid. Okay. Yeah. So pseudoplastic example will be blood. Dilatant sample will be like a sand in the water. Right? These are the very straightforward information. And for non-Newtonian, we will use this equation. So for non-Newtonian, shear stress equal to K, and then we power the shear rate here. There's an n, exponential n here. Okay. So for Newtonian, your n is 1. Yeah. Your Newtonian, the n is 1. Okay. Okay, so this equation is important for you to mathematically define what is non-Newtonian fluid. Okay, so if your n, or you call it as a flow behavior index, if your n is more than 1 or less than 1, then it's a non-Newtonian fluid. If your n is 1, then it is a Newtonian fluid. Okay, so this is how you differentiate or mathematically define Newtonian and non-Newtonian fluid. Okay, quite straightforward. Okay, then let's see. Okay, another way we write the shear stress. The relation between shear stress and viscous the shear rate is through this mathematical equation, but it's sufficient for you to memorize this one. Yeah. Now the next one, after we define Newtonian and non-Newtonian, the next one we look at surface tension. So what mean by surface tension? So if you drop a droplet of water, or drop of water on a glass, then you will see the behavior of that droplet will behave either on the left hand side or right hand side. So we as an engineer, we like numbers, or we like to quantify or give definition to a certain terminology. So what mean by weighted wet surface and not wet surface? So we define by an angle given between the surfaces and the normal intersection of the curvature of the water, of the surface. So if the theta is less than 90 degrees, then you are having a wetted surface. If the angle is more than 90 degrees, then we define that we are having a non-wetted surface. When the surface is not wet, it's just you just have a water droplet above the surface. But if your angle is less than 90 degrees, then we can say that the water droplet actually make the surface wet. Okay, so this is how we define a wet and non-wet surface. This behavior is because under the effect of surface tension. Okay, so what is the application in our daily life? Why do we need to aware of the surface tension, or what are the apparatus that we use or make the effect of surface tension useful? So there are two. One is manometer, one is barometer, or sometimes we use as a thermometer. In general term is that we have a tube that fill in the water, or not water, fill in the fluid. So for example, there's a capillary effect under because of the surface tension. Then you have a two observation. So if you put a tube inside a liquid or fluid, if the angle, if the theta is less than 90, then it will push the liquid or fluid a little bit higher compared to the reference surface. There's a delta H there. Okay, there's a positive H if your angle is less than 90, while if your angle is more than 90 degree, then your the curvature of the fluid will fall below the reference surface. The delta H will below the reference surface. So there are two observations because of the surface tension. The curved meniscus, will be either inverted like this or inverted like this. So there are two behavior. So when you draw a free body diagram later to solve problems, be careful when you draw. Don't pay a little bit more attention on the curvature. So if it's 90 degree, it is a smiling face. Less than 90 degree is a smiling face for inside the tube and outside the tube. If it's more than 90 degree, then it's a sad face. And same with the contact with the tube outside. So be careful on the curvature for the meniscus. Yeah? So you can either have capillary raise or capillary depression. So there are two behavior, okay, depending on the degree of in the fluid there. So quite straightforward. We look at one example. So this is under question 26 in your tutorial question. So you're given a diagram. So you're having a fluid. You pour the fluid inside the a beaker or the container, and you're able to measure the height of the meniscus, and you're given a force of the surface tension force of a certain angle, theta, the magnitude given by a formula, stress times the pi times the diameter of the capillary. And there is a gravitational force. And gravitational force always like to attract mass. So there's a rho GV force going down. And again, our axis Z is pointing up. All the direction going up is positive. And we refer going up is Z-axis. So what does the question ask us to do? It asks us to create a graph showing the capillary raise or fall of the column of water or mercury, respectively. It asks you to draw a graph for water and mercury as a function of tube diameter. Find the minimum diameter for each column required so that the height magnitude will be at least less than 1 mm. So this one, the delta H will be less than 1 mm. You need to calculate the D here. For two scenarios, one is water, one is mercury. So how do we start? We look at the information we have. So we have a tube dipped in a liquid, and we have two types of liquid, water and mercury. We need to find an equation that relates delta H to D. So you need to call out an equation. Yeah. So we will apply equilibrium, law of equilibrium, or free body diagram to solve this one. So we apply equilibrium to the system. When you have an equilibrium system, meaning all the force inside the system equal to 0. In this case, since we are given the axis direction, so in our equation, we write sum of all the force in z direction, sub z means in z direction, equals 0. And we put everything in this equation. So from here, there are two forces here. So the next step is that you need to write these two equations inside here. So again, direction is important. All the direction going up is positive, all direction going down is negative. So, and we have a force in the diagram here. So theta or sigma pi d, this one is the force, surface tension force that given. So we know that this having an angle, and this is a resultant force that we have. So all the forces with the direction we can derive, or we can split into two components. So we can split in vertical and horizontal. So you need to call your trigonometry idea, how to find the one on the left, how to find the one on the right. So you have to call back what is tangent, what is sine, what is cos. Yeah. So there are two assumptions. We measure to the middle of meniscus, meaning we will only measure up to height here, and we ignore the volume over here. Yeah, the small volume, extra volume here we ignore. Okay, so we start solving already. So you try to put in all the equation. We only look at z direction. So this force, cos theta, is become a vertical one, and rho g delta v with a head with a line in the middle means this is a volume, change of volume, equals 0. Okay. Any one of you need me to explain why there's a cos theta there? Let me know now.
No, sir.
Good, huh? Everyone is good, huh?
Yes, sir.
Okay, good. Seems that three of you are strong in mathematics. This is a good news. Okay, we ignore the volume in meniscus reason. So our V, so you just calculate the volume for a cylinder. So how you find volume for cylinder? You calculate the cross section of a circle times the h. So area of the circle is pi r square or pi d square divided by 4 times the h. You get the volume of the liquid here. So you substitute this one inside the equation earlier, and then you rewrite the equation in terms of delta h and other terms. All right. So because we want to find the relationship delta h and d, so you rewrite this equation after you substitute the delta v here, delta volume here, inside this equation, you rewrite in this form. So that's quite straightforward equation. There's no complicated equation so far. Only challenge one is this equation. Right? Some of you might, when you look at the question, you might ask, hey, why suddenly there's an equation? This is the surface tension force. And then, yeah, how to find the sigma and theta for water and mercury? This one you need to refer to Appendix A, Table 4. Appendix A, Table 4. So I already upload the appendix in Moodle, so you need to download it because you need it for your coming test and also final exam. Okay, so how does the A4 table A4 look like? It look like this. So in the table you have the liquid. So one is in contact of air, one is in contact with water. So you need to be careful when you refer to the table. One is air section is with air, B section is with water and the value is different. So don't refer to the wrong one. And yeah, so the information is self-explanatory. So the information you have in table A4 is surface tension and also contact angle. And contact angle only you have two data for two medium here. One is for mercury, one is for water. Water is 0 and mercury is 140. And if it's contact with water, then you only have one data for mercury. So in our case, we only have the air and liquid. So we look at the first portion here, and we only need to extract for mercury and water because the question gives us to solve mercury and water. Okay. So I just highlight something on the screen here so that you can see. So mercury 484 m n over m unit. What mean by small m is a milli. So milli is 10 power negative 3. So if you don't know, you can also refer to the bottom of the table. There's a explanation there. So there's no reason why you cannot do this when it comes to tests. And most of the time, the mistake will be the conversion of the unit. You panic already in test and you forget to change the m into 10 power negative 3 in your calculation. So these are the student mistake or error when it comes to calculation. Okay, so we have these four numbers. Yeah, so for water from this table is 72.8 milli-Newton over meter. Angle is 0. Mercury is 484 milli-Newton over meter. Theta is 140. Okay, so quite straightforward from the table. So we're back to the question and the equation that we derived just now. Delta H equal to 4 sigma cos theta divided by rho GD, and the information we get from table 4 just now. So you can plot the graph if you want. Yeah. So you have the constant value of all this. For water, you substitute all the value inside there, cos theta, right? So you will get the constant value for delta H and the D here, 1 over D rho G. And just a reminder, on the screen here, I write beware of the temperature. So when you refer to the table for either for the specific gravity or the temperature or the density inside the table, A1 and 8, be careful on the temperature, make sure they align to each other. So because the question do not mention temperature, so you need to be careful. When it comes to test, temperature will be mentioned so that you won't make any mistake there. So in this case, since you are referring A1 and A8, and A1 give you 20 degrees C value, so you go and look at 20 degrees C property. So this is the highlight, for you. So again, two medium. One is mercury, one is water. So because in table A1 we don't have water here at 20 degrees C, so but there's a big table for water. So both in one is in unit SI, one is dimensionless specific gravity. So you copy 13.55 and all the density at 20 degrees C, 998 for water, kilogram over meter cube, and you have the viscosity and so on. So to find the density of the mercury, you just take Sg, specific gravity, times the rho of the water. Yeah. So in this case, we take 13.55 times 998. Then we'll get in kilogram over meter cube. So you pull the number back to the drawing board again. So you have for this one is for this one for water, and mercury is this one. So again, mercury, the angle is 140. You do the calculation, you get the definition. So one, you get negative, one, you get positive. Why you get negative? Because cos 140 is a negative value. And just now, we also saw that under the surface tension, you have different meniscus behavior. One is a smiling face, one is a sad face. So when you plot the graph, right? So before we move to the next slide, any question on the equation on the screen here? Anything that look?
No, sir.
No, good, huh?
Yeah, it's good.
Oliver, you all right?
Yes, sir.
Okay, good. So you get a negative, and the unit here is mm. Yeah? Unit here is mm. So of course you can put in meter, because after conversion, after I do all the round up, I get mm because it helps us to better understanding on the question itself. Okay, this one. Okay. So from here you can solve the answer, because from here we want to find the magnitude of the height when your magnitude of the height is less than 1 mm. So what you do here direct from the equation is you replace the left hand side with 1 mm, and then you solve for the D. The first one, for the water you get 2 point something, for mercury you get 1.1. Of course from the graph, if you want to plot also can, but this is a more straightforward answer. Okay, we solve for the first tutorial question for under surface tension. Any question so far?
No, sir.
Good, eh?
Yeah.
Okay, good. We move forward. Okay, so the next one is the understanding of classification for fluid. So under your tutorial question number 27, there are some blank that you need to fill in. If we study fluid mechanics, we can split into two categories. One is inviscid fluid, one is viscous fluid. So inviscid means you don't have friction. Viscosity constant value equal to 0. So you don't have friction. Viscous means your the mu, the viscosity. It's not that you don't have friction, but the viscosity constant is not 0 when it comes to viscous. Then you will study laminar, what is turbulent, and then after that you will study internal flow and external flow. Under inviscid category, there are only two. One is compressible, one is incompressible flow. Compressible means you're able to compress it. Incompressible means it do not deform. Yeah. So this diagram is also quite straightforward. Okay, we put a diagram to this to one side, just to a little bit more explanation on viscous and inviscid flow. So inviscid means you don't have friction. Textbook term we use frictionless, but if you write in the exam, you can write have no friction. There's no friction in the system, or there's no friction in the flow. Okay. So the one under diagram in tutorial question number 28, there's a diagram there. So on the left, if there's no friction, you will have a symmetrical flow from before and after a round body. Okay? This is under inviscid flow observation. And then if you have a viscous flow, means when you have a friction, a surface friction effect between the contact of the flow and the sphere here, then there's a point of separation and there's a wet region after the cylinder here, then this is fall under viscous flow. Okay, so this is just a general observation. What is in viscid flow, what is viscous flow. So this one you will see in the experiment later on. Okay. And yeah, this graph is just a 2D graph that give you a general idea how fluid behave on a surface. So when you have a fluid flowing from the left to right, so if your fluid touch the surface, because you have a viscous effect, friction is a resistant force to the movement. So the contact surface, the contact of fluid and the surface here will give you zero velocity. There's no velocity at the contact point, and then slowly the velocity will pick up until a dashed line here. A dashed line here, we will define it as a boundary layer. So we'll look at boundary layer later on in later chapter. But at the moment, the dashed line here, you just imagine there's a region. After the fluid pass this region, all the velocity will remain the same. Means there's no loss of energy. The velocity at this point was same as this point. Okay, and this region we call it inviscid flow. The one that having the effect of friction, we call it viscous boundary layer. Okay, so I think this one also quite direct. And differences between laminar flow and turbulent flow. Laminar flow means that the velocity does change towards time, and you only have one direction. So this is a vector mathematic order. So V equal to UI means U means x direction, I means x direction unit vector. So U means a magnitude of your velocity in x direction. I is the unit vector for x direction. If you have a turbulent, then you will see there's a change of your velocity component in XYZ component. So this is a mathematic presentation, how you define a turbulent flow and laminar flow. Okay, so by looking at the mathematic model itself, you can tell whether you have a laminar flow or turbulent flow. Okay, and this one will come to simulation. If you use simulation, then this part will come into important place. The next one will be compressible and incompressible flow. So again, if the flow is not able to compress, means incompressible flow, there's no change of volume. So how do we define density? Rho equal to mass divided by volume. Mass is in kilogram, volume is in meter cube. So if you're not able to compress, for example, a cube, the mass doesn't change, volume doesn't change. So if you don't able to compress the element, then the density that you use in the equation later on, it will be the same before and after. So it means that if you have a compressible, later on you can simplify the equation by taking out all the density inside the equation later on. Okay, but the main concept is that when inside the question, you see that if you're having an incompressible flow, you write a sentence where you write rho equal rho 1 or rho 2 means 0.1, 0.2 equal a constant. This statement will give you 1 mark. If the question you see there's a key point mentioned incompressible, you straight away you write this equation. Rho equal to constant or rho equal to rho 1 equal to rho 2 equal constant, you will straight away get 1 mark without any calculation. This is just evidence of your understanding what is incompressible. Okay, some free mark here, yeah. Okay. The next one is compressible. Is the opposite definition. So if you're compressible, then you cannot ignore the density in your calculation. Other definition for bulk compressibility, modulus elasticity, this one you refer to Appendix A. Yeah. So bulk modulus given by EV, V represent a volume, means it's a bulk modulus, equal or equivalent to dP over d rho over rho. Change of pressure versus the differential of your density. Okay, so there are two sets of calculation here. One is the change of pressure, another one is the change of your density. So bulk will deal with your density and pressure. Okay, yeah. So if you refer Appendix A, there's a bulk modulus there. In gigapascal. Pascal is Newton over meter square. So giga is 10 power 9. So when you do calculation, be careful on the conversion. Okay. So you have water. Water, the bulk modulus is 2.44 giga-Newton meter square or gigapascal. Specific gravity also given. So again, you see the water, the specific gravity is not 1, but it's 0.998. Why? Because it's under 20 degrees C. Okay, so be careful on that. Why do we need to consider compressible effect in a liquid flow? There are some accident or there are some after effect if you ignore the compressibility in your design later on. I will show you the two effects. One is called water hammer. One is called cavitation. So water hammer, what do you mean? Water hammer is the one that you see on the screen now. It means that there's a certain shock wave or there's a certain shock or increase of pressure in the pipe if you suddenly close the valve. So if you have a running water, you suddenly close the valve, you will have a shock. They have a peak. There's a jump of pressure inside the pipe, and sometimes the pipe will break if you're not careful. So if you are oil and gas engineer and you are designing a pipe delivery system, so we will try to avoid water hammer effect in the oil pipe, right? Because when you transfer water from the oil platform itself, oil itself will mix with water and oil. So if you suddenly close the valve, then explosion will be happen and crack will be happen in the pipeline. Okay, so water hammer is just a behavior of liquid under compressibility effect. When you try to, because when you close the valve, the water or the fluid is suddenly compressed at a certain point. Okay, another behavior we call it cavitational. Cavitational link with bubble. Right, the word itself linked with bubble, water bubble. So why we need to be careful on cavitational in a pipe system or when you study about fluid. So this is a diagram on the screen now. Is a propeller of a ship. So this is in a slow motion. So as the blade rotates, the tip of the blade there will generate a small bubble because of the compressibility of the compressibility effect. Because as the blade travels through the fluid, the mechanism itself will compress the water molecule at a certain point. Because of the speed of the rotation, the molecule in front of the blade was being driven and compressed, and it will generate the a scenario or the effect called cavitation. This is not what we want in water, especially you are building a submarine. This one will become a trace of the existence of your submarine. Okay, And if in water, in a ship, so this one will also generate wave inside the water. Then it will create sound, and also the bubble itself will create disaster to the ship structure also. Okay, so just an idea. Compressibility effect, you have two that you need to pay attention when it comes to pipe design or anything that deal with a liquid or fluid. One is water hammer, one is cavitation. So sometimes in your house, when you suddenly close your pipe or your valve, then you'll hear a sound in the wall. So it's also under the effect of water hammer. Okay, so these are the two effects. Then again, as an engineering student, so we also like to quantify something. How do you know in liquid we need to use a compressible or non-compressible scenario? We will use Mach number. Mach number is dimensionless unit, or there's a dimensionless parameter where Mach number is a number of a ratio of local velocity divided by local speed of sound. V divided by C. Again, for the module, if you see capital V, it represents velocity. If you see the V with a center line in the middle, then that one represents volume. So Mach number equal to V divided by C. C is the speed of sound. And if the number less than 0.3, it falls under category incompressible. So this is a magic number that you need to memorize when you link with fluid, especially when it comes to simulation. When you use simulation tools, you need to select whether you want to simulate incompressible case or compressible case. Or when later you deal with equation, a lot of equation, for example, nervous stroke equation later on, you need to know whether you want to use a compressible approach or incompressible approach. So this is a guideline. We look at Mach number. You calculate, you take the local speed of the fluid molecule divided by speed of sound, local speed of sound. You get the number. If the number less than 0.3, then straight away you go and use incompressible equation. So from this statement, you know when you need to use a compressibility. If the Mach number more than 0.3, then you use a compressible equation. Again, Mach number less than 0.3, it falls under incompressible scenario. Okay, internal, external is quite self-explainable. So yeah, internal means inside the pipe. External means like the flow in the immersed body, like a boat traveling above the seawater. That one is external flow. Yeah. Okay, we have clear chapter 1. Let me stop the recording.